Continuing with section 2.6, let's look at example 3 now. For the speeding fine function, evaluate f of 74 and f of 75. F of 74 would be the fine you would be charged according to the function for speeding at 74 miles per hour. So if we have x equal to 74, then we fall in the range x between 55 and 75. So that means we would use the first part of the function to compute the function value. We can only use one part or the other. We can't use both. So we have to choose the correct part to plug into. In this case, that would be the first part. So what is f of 74? Well, it says it would be 50 plus 3. X is 74, so 74 minus 55. That'll multiply the 3. So simplifying, that's 50 plus 3, and 74 minus 55 is 19. In other words, at 74 miles per hour, you are speeding at 19 miles per hour above the speed limit. So it's $3 for each of those 19 miles per hour plus the $50. 19 times 3 is 57. So it's 50 plus 57, which is 107. In other words, your fine for traveling at 74 miles per hour in a 55 zone is $107. Now f of 75. Well, at 75, the rule changes. If you're greater than or equal to 75, then you're going to use the second part, the second piece, to evaluate the function. So this would be computed as 150 plus 5 times 75 minus 75. Well, this is going to be simpler. It's 150 plus 5 times 0. So if you're caught speeding at 75, you owe $150, but you're not going above 75, so you don't owe anything above that, anything beyond that. So it's just 150 plus 0, $150. Now, the 0.75, 150, that's just this point we have right here on the graph. I'll just kind of darken that in a little bit. That's the point we just found. What about 74, 107? Well, that would be about right here, just before we get to that open point. And what we can see described when we evaluate f of 74 and f of 75, we can see this big jump that occurs at 75. At 74 miles per hour, the fine's $107. At 75 miles per hour, it jumps $43 to $150. So there's that big jump discontinuity that's being described when we compute these two function values. One other comment about the graph. The graph of a piecewise function must pass the vertical line test. It's a single function. The function has more than one piece, but it's treated as a single function, and its graph must pass the vertical line test for functions at every point, including at 75. And you can see at 75, if you put a vertical line where x is equal to 75, it will intersect the graph only at one point, at that point right there. You have the other point open because you cannot have two different function values for one value of x. For every x there must be one and only one y value. Now let's continue to example 4 and consider a different example, a different piecewise function. This function has 3 pieces. There's no context to this. This is just one I made up. So when x is less than 0, the function is defined to be 2 minus x. When x is greater than or equal to 0 but less than 2, it's x squared. And when x is greater than or equal to 2, f of x is equal to 4. So it's defined in 3 pieces. Let's evaluate f at 3 different values of x. First of all, f of negative 1. If x is negative 1, then x is less than 0, which means we compute the function according to the rule 2 minus x. So f of negative 1 would be computed as 2 minus negative 1. That is 3. And I'll just put here next to this to remind you, since negative 1 is less than 0, we compute the function value using the first piece of the function, f of 0. Well, if x is 0, then x lies in the interval greater than or equal to 0, less than 2. So here, we would use the second piece, x squared. So that would just be 0 squared, or 0. F of 0 equals 0. So this would be, since our x value, 0, lies in the interval between 0 and 2. So we only use one piece of the function to compute the function value in each case. Finally, f of 5. Well, our x value of 5 is greater than or equal to 2. So here we're going to use the third piece of the function. So f of 5, well, it would just equal 4, because for any x greater than or equal to 2, the function value is always 4. It's constant when x is greater than or equal to 2. So this would be, since 5 is greater than or equal to 2. We use the bottom piece. Now let's sketch the graph of f. And to do this, we'll actually be sketching 3 graphs. Beginning with the part of the function defined for x less than 0, which is f of x equals 2 minus x. I'm replacing f of x with y here so that I can make a table of points. And I'm going to choose some x's less than 0. Just make a little table here and compute the y value for each x that I choose. Now, even though it says x is less than 0, I'm going to use 0 itself to establish an endpoint for the graph. And this is something you should do as well if you're sketching one by hand. And then how about if we choose maybe negative 1, negative 2, and negative 3 as well? The y values would be as follows. 2 minus 0 is 2. 2 minus negative 1 is 3. 2 minus negative 2 is 4. 2 minus negative 3 is 5. So we would plot those points, except at 0, 2, we would use an open point. Like so. There'd be an open point there, and then let's plot our other points. Negative 1, 3, negative 2, 4, negative 3, 5. And you can see that the graph is just going to be a straight line. extending up like so. So that's the first part of the graph. Then we move to f of x equals x squared for x between greater than or equal to 0 and less than 2. So once again, I'll make a little table. And here I'll just need to choose 3 values of x. I'll use 0, of course. I'll use 1. And I'll use 2, even though it says x is less than 2. We'll use 2 anyway to establish an endpoint for this part of the graph. So we square the x to get the y value for this part of the function. 0 squared is 0. 1 squared is 1. 2 squared is 4. So 0, 0. Now this point is on the graph, so we use a solid point there. It's greater than or equal to 0. So we use a solid point. Then 1, 1. And then 2, 4. And at 2, 4, we'll use an open point, an open circle, because technically x is less than 2 but not equal to 2. So that just establishes an endpoint for the graph. So we use an open circle there. Y equals x squared, you may recall, is a parabola. So it's helpful to remember that so we know what the shape looks like. This goes back to those basic functions we looked at earlier in the notes. So we get this piece of a parabola. And then for x greater than or equal to 2, f of x equals 4, which is a constant function. And again, I'll just plot some points here. 2, 3, 4. The y value is always 4 here. So we always get 4 for the y value. Now, 2, 4 would basically fill in the point that was left open from the previous part. Then we have 3, 4, and 4, 4. And you can see it's just going to be a horizontal line that extends to the right. I'll put an arrow there. I'll put an arrow there as well to show that those parts of the graph continue indefinitely to the left and to the right. Notice how the graph will, as a whole, pass the vertical line test. For every value of x in the domain, there's only one value of y associated with a given x. So you want to make sure that the graph as a whole passes the vertical line test. The domain, as you can see, is the set of all real numbers. We have values of x less than 0, between 0 and 2, and greater than 2. We have all values of x. There are no values of x for which we cannot compute a function value. So the domain is a set of all real numbers. The range, notice, is restricted to non-negative values of y. You notice the graph never goes below the x-axis. There are no gaps in the y values that we can compute. We can have any y value greater than or equal to 0. So the range is the set of all y greater than or equal to 0. That is, bracket 0 to infinity. So that concludes section 2.6.